p subtract with y, right? Here I have to take the partial derivative because I have y and z two variables. So when I take the derivative with respect to y to this expression, I'm leaving with p sub y. You agree with me? So this step I'm take y derivative. But I want to make this guy to be equal to what is given in the conditions. What is given in the conditions, because this is a conservative vector field, is the gradient vector of phi function. So this has to be phi x, this has to be phi y, and this has to be phi z. All right? So this one has to be equal to xz plus 1. So this is from the condition, or from the assumption in the problem. Okay? So this equation is coming from taking y derivative. Set the equation and make these two equal are definitely coming from the assumption of the problem. Okay? And then I'm going to extract what is useful for finding p of y. All right? So this equation tells me p sub y has to be equal to 1. Okay? P sub y has to be equal to 1. But p is a function depending on y and z. So we're playing with the same procedure one more time for finding p with respect to y. All right? So make it clear this one is depending on y and z. You take the partial derivative with respect to y, you're getting it equal to 1. So this guy has to be equal to I definitely have to have a y when I take the derivative with respect to y. I'm getting a 1. All right? But I also have a constant. But this constant is no longer going to be related to y anymore. All right? Because in the whole point of second step is to eliminate the dependence on y. So I have a constant, but this constant can only depend on z. So I have a constant q, but it is a function of z. Okay? Now I see some puzzle faces. Questions? Okay? So if you think about this whole procedure, in every step we're playing around with exactly the same principle. The principle is, if I have the derivative information of whatever function, okay? If I have the partial derivative information about any function, then it tells me when I take the partial derivative with respect to this particular variable, all the other variables are constant. I'm getting exactly 1 here. So you are trying to find the antiderivative exactly as what you did in a single variable case, but the only difference here is when you stick in this constant here, this constant is not a real constant. This constant is a constant including the variables you regard as the constant. Are you with me? So when you think about taking derivatives, you take the derivative, you throw away all the variables as constant. And this constant have to be apparent in the constant of the antiderivative part. Okay? So Sola, you have questions?
What does it say from the assumption in the...
Oh, the assumption is actually here. So this is equal to my gradient vector, which is equal to phi x, phi y, and phi z, which means phi x is equal to yz plus 2x. I'm using the assumption that phi y is equal to xz plus 1. That's why I make these two are equal. Are you with me? So that is what I mean. The assumption here, thank you, yeah. So this is the assumption I use phi y is equal to xz plus 1. Okay? Okay, now I will be able to put the two steps together. I have essentially phi of x, y, z has to be equal to x, y, z plus x squared, and then I have p of yz to be written as y plus q of z. This is what I got from the first two steps. All right. In the first two steps, I already found all the dependence of this phi function upon x and upon y. That is the reason why I only have one unknown part, but this unknown part is only depending on z. Okay? So in the very last step, naturally, I want to figure out what z is. So what this z unknown part is. So I have to take the derivative with respect to, so take the derivative with respect to z. take z derivative. So if we take the z derivative with respect to this expression, what do we have? It's equal to xy plus q prime z, all right? Now I can further use the usual derivative here because q is only a function depending on one single variable. So I can use q of z. This is getting from taking the derivative of this expression in the second step. And then I have to use the expression coming from the condition here. Okay? So this is an assumption coming from the condition given in the very beginning. So phi of z has to be equal to xy minus 1. So this one has to be equal to xy minus 1. So this is from the assumption. From the assumption such that phi of z is equal to xy minus 1. So this is a pretty easy part. I figure out q prime z has to be equal to minus 1. So z has to be, I'm sorry, q of z has to be equal to minus z plus, now we have a real constant here. So this real constant is not going to depend on any of the variables before. So in the end, I put all the things together. I have this phi of x, y, z has to be equal to x, y, z plus x squared plus y minus z plus a constant z here. So this is going to be the potential function. Okay. So this is the potential function. Again, you exhausted a lot in these 3 steps finding this potential function in the end. I want to take the derivative to check. So checking whether the potential function is the real potential function is considerably easier comparing to what you have done in the 3 steps. Because now I'm simply taking 3 derivatives. X derivatives, what is? Yz plus 2x. So this one is checked out. Y derivative is xz plus 1. This is also checked out. Z derivative is xy minus 1. So this is also checked out. So always check your potential function. Always check your potential function. Okay? Important things, I say it 2 times. Okay. Any questions on how to check whether a vector field is conservative and how to find the potential function? So now, what is so special about the conservative vector field? And sometimes you may wonder, why is it called a conservative? Right? You wonder about that. Why is it called conservative? So the reason it is called conservative is related to the other very important property of this kind of vector field. So if a vector field is conservative, then we can take the line integral of a smooth curve f at t dx, where the c is r prime t from a point A to a point. For instance, if this is R3, if this is R2, this is a line from a point A to a point B. Okay? So we learned about how to take the line integral here. All right? We'll learn about how to take the line integral here. So in order to evaluate a line integral of a vector field with respect to a curve in R2, we have to find the parametric equation of this curve and then translate everything with respect to the parameter. All right? We have to translate everything into the parameter, and then we're taking a single variable integral with respect to that parameter. Have you still remember that? Mm-hmm. Right? So you still remember. That's good. So given any vector field and given any curve, we can find the line integral with respect to this curve of this vector field. There is another notation about this line integral. Those 2 are equivalent. Okay, those 2 are just 2 different notations for the same object. Okay, This is also the line integral with respect to this curve of vector field. Okay? So now here is the important part. If this vector field is conservative, then this line integral is nothing but the difference between the function values of its potential function. So here, phi is the potential function. Okay? Here, phi is the potential function. In other words, if we're evaluating the line integral of a vector field with respect to a curve, then it is simply equal to the difference between the function values of the potential function. And this formula is only true if the vector field is conservative. And if you look at this equation, this equation seems very familiar, right? So in the very beginning of this chapter, I mentioned about the biggest goal in this chapter, which is to introduce fundamental theory of calculus in multivariable case. Fundamental theory of calculus, the principle or the moral information you want to extract from a fundamental theory of calculus is you're taking the integral of something in the interior. It equals the difference of a different function on the boundary, all right? So in the simplest case, if you have a closed interval, you're taking a single variable integration with respect to this closed interval. It equals the difference of its antiderivative function on the two boundary points, all right? So this one seems extremely similar. I'm taking the integral in the interior of a line. It equals the difference of its potential function on the boundary points, all right? So this is indeed the fundamental theory of calculus, of conservative vector fields. Okay? So this is the fundamental theory of calculus of the conservative vector fields. There's one remark I want to make. Given any vector field, given any curve, because this curve is written down in a parametric form, there's always an orientation inherent in this smooth curve. So the reason we have this difference, when we have a difference of a function value at different points, we have to make sure the initial point and the terminal point. All right? So how do I determine A and B, which one is initial, which one is terminal? How do I determine, given these 2 points, A and B, on the boundary of a smooth curve, which one is the initial point, which one is the terminal point? We have this orientation in the curve, all right? So the way of determining A is the initial point, B is the terminal point, is exactly coming from the fact if the orientation is going from A to B. Are you with me? So when you have a curve, this curve is written down in its parametric form. The parametric form has the advantage over x, y equations, is that it can give you the orientation of the curve, all right? The orientation of the curve is given by the parameter is increasing. If the parameter is increasing, you see A is the initial point, B is the terminal point, because the orientation says A is the one you begin from increasing your parameter D. And it increases, then the point will move from A to B. Then I see A is the initial point, B is the terminal point. That was me? So A and B, in order to determine, will be having the orientation of the curve. Okay, so then I have another remark. Let's say I have a curve, different curve. It also goes from A to B, but with different passes. So if I have 2 points, A and B fixed, and I'm doing these 2 different curves, and I compute the line integral of the same vector fields, but with respect to 2 different passes, according to this fundamental theory of calculus, these 2 line integrals have to be exactly the same. Now with me? These 2 line integrals have to be exactly the same because it is always equal to the difference between the function values at those different points. So if you don't change this initial point and terminal point, you can go whatever passes going from the initial point to the terminal point. you're gonna end up with the same line integral no matter which path you go. Are you with me? You can go as crazily as you want. But as long as you go from the initial point and end up with the same terminal point, this line integral with respect to any path is always the same number. And this is indeed the reason why this vector field is called conservative. Okay? It is independent of the path. So this is independent of the path. Okay? So if a vector field is conservative, it has a very, very important property, such that all the line integrals lining together 2 points, as long as you indicate A is the initial, B is the terminal. All the passes go from the initial point to the terminal point. The line integral of the vector field is invariant, or it is independent with respect to the passes you're taking. Okay? Are you with me? Okay, I'm going to elevate it even more. If I have a conservative vector field, and I have a curve, and this curve is closed, think about what it means for a curve to be closed. So from the initial point and terminal point of view, if a curve is closed, if and only if I begin from the initial point and then I go back to end up with the same point, all right? So you can understand a closed curve as the initial point coincide with the terminal point, okay? So if C is closed, then the line integral is going to be equal to 0, okay? In other words, if this line or this curve is closed, then the initial point is the same point as the terminal point. When I evaluate this line integral by the fundamental derivative calculus, it is equal to the function difference between these 2 points. But these 2 points are the same point. That's why this right-hand side is going to vanish. So the line integral of a conservative vector field along any closed curve is always equal to 0. Okay? This is a very, very special property of a function of a vector field. Okay? And this notation, as long as C is curved, a lot of cases is written down in this form.